Hi and good day. My name is Farra Fatini, Lee, and my metric number is 251111132, and I'm from Group 6. And my audio file name is 3 Hertz Sign, and I want to present Laboratory 2. Our research has how about material composition affect recorded sound wave amplitude at a feet distance, and we aim to investigate and compare plain versus thermofoil box dampening. And our independent variable is the box material, and the dependence variable is the recorded amplitude. And we hypothesize that if a thermofoil board is used, then the recorded amplitude will be lower because it a foam and foil provides superior acoustic damping. We're moving to our experimental setup. We follow a strict 4-step procedure. First, we place the sound speaker inside the plain board. Second, we position our smartphone microphone exactly 10 centimeters away from the interior of the box using a physical ruler to ensure precision. Third, we play our 300 Hz sine wave audio signal at a 100% volume rate and recorded the resulting peak amplitude. And the last one is we repeated this entire process using the thermobots while meticulously keeping both the speaker and the microphone at the exact same position, is 10 centimeter away. And then to ensure this experiment can be exactly replicated, we maintain two critically safety and operational precaution. And then the speaker physically orientation was kept completely identical across both trial to eliminate directional wave bias. And then we need to the entire process was conducted in a strict silent room to prevent us outside background noise from contaminating our microphone data or causing a false voltage peak. And then let we examine the raw data collected from our trial presented here with a precise unit and significant figures. So has a display in our primary data metric and bar chart. The plain box recorded a peak amplitude of 0.07025 volt and root means square signal power of 0.07400 volt. And when we switch the thermobox setup, we observe a massive drop in electrical energy. The thermobox yield a peak amplitude of just 0.0368 volt and true RMS signal power of 0.03317 volt. And if we're looking at our frequency metric, the plain box registered a dominant frequency of 2999.96 Hz, while the thermobox record 300.04 Hz. So this confirms that our 3 Hz input signal remains steady and upward across both trial. So ensuring that our data insulted the dampening effect rather than the sound distortion. So this brings us to our accurately plot graph, and the top graph display our time domain comparison scales from 0.4 to 0.45 seconds. The blue wave represent the plain box, and the red wave show the thermobox. And you can visually see the microscope two waveform compression in the thermobox. And the bottom graph display the frequency domain spectrum, and it features a shaft. And then the last one is the bottom graph display the frequency domain spectrum, and it features a sharp, clear, tighter, and axis level in magnitude versus frequency. And we notice that both curves spike exactly around the 300 Hz mark, visually demonstrating that geometry dampens amplitude without shifting the frequency peak. So to process this data accurately, we also custom scalar script. So the code work by first validating and loading of raw audio files, is handle channel conditioning, and calculates the time domain's RMS power, and then apply a fast Fourier transform to convert the audio into the frequency domain. And finally is how to extract the peak voltage level and output our comparative attenuation metric. So this brings us to our accurately plot graphs. So our quantitative analysis strongly support our original hypothesis. By connecting our result directly back to our claim, the data show that the thermofoil box caused an absolute voltage peak drop of over 0.033 volt, which translated to a massive 47.82% peak exhausted emission. This occurred because the multi-layer form and foil construction absorb and scatters escaping acoustic energy for better than thin single layer plain cardboard. And however, we must evaluate our limitation and potential error with clear reasoning. So a primary limitation is our single frequency constraint. We just only test a low frequency 300 Hz tone, meaning that result cannot represent how this specific material reacts to high pitch and high frequency sound. And then the box were tested without matching their exact wall thickness, leaving a slight as to whether the dampening stems purely from material composition or structural thickness. And regarding experimental error, slightly ambient room noise could still mingle with our microphone reading, and minor acoustic leakage might have occurred through seam or small gap in the box screw too. And the last one is a real world application. So in terms of real world application, this finding validate the practical use of multi-layer foam and foil composite in industrial acoustic engineering, such as creating soundproofing, insulation for loud machinery or line speaker enclosure to capture internal standing wave and improve audio clarity. And let we move to our conclusion, and this is our conclusion. In conclusion, this laboratory experiment successfully answer our core research question. We have definitely proved that the material composition of enclosure play a direct role in controlling escaping sound wave energy. So to summarize our key finding, the thermofoil box provided a highly substantial 47.82% acoustic attenuation compared to our plain cardboard box baseline, and this result completely validate our hypothesis. The combined dense foam and relative foil layer deliver vastly superior acoustic damping and structural absorption without causing any underlying frequency distortion to our tone. So that concludes my presentation and laboratory 2. Thank you very much for the time and attention.